Here we're looking at example 11 from our 3.1, 3.2 set of notes. We're asked to solve this system of equations. Now we notice one thing right off the bat that kind of separates example 11 from our previous examples is the fact that we have this absolute value function. Now we're still going to go ahead though and treat things exactly the same way when we're solving them as before though. Notice how y is equal to this piece, this negative absolute value of x minus 2 plus 3. Well, we already have a variable solved for, and from that, then we can go ahead and just use our substitution method, where we're going to take this negative absolute value of x minus 2 plus 3 and throw him into our second equation anywhere that there is that y, because again, this piece is equal to y. And as a result, y is equal to y, which is also equal to this negative absolute value x minus 2 plus 3. So we're going to go ahead and take that and substitute him in to our second function. We end up then with x minus 2 times negative absolute value of x minus 2 plus 3. And that's equal to negative 5. Going ahead and distributing in this negative 2, we would end up then with x plus negative times negative, that's why we have a plus, 2 times the absolute value of x minus 2 plus negative 2 times positive 3 would be a negative 6. So we can really get rid of this plus. And that's equal to negative 5. Now, I've had students in the past ask me, well, don't you distribute that negative 2 into these items? And the answer is no. We're going to treat this entire absolute value, just like we've mentioned before, as one big x. All right, so only the number on the outside would get multiplied by that. In this case, it was negative 1. Now let's go ahead and try and solve for x here. We end up by adding 6 to both sides, so that's x plus 2 times the absolute value of x minus 2 is equal to 1. And one issue that we're running into here is the fact that we have this x on the outside, and we've also got this absolute value of x. Well, what we're going to go ahead and do is still subtract this x over to both sides. So on the left, they cancel out, leaving us with 2 absolute value of x minus 2s is equal to negative x plus 1. Now, in mathematics, we're typically used to having the same variable all on the same side, and then all the other stuff on the other. In this specific case, though, it's actually pertinent that we have x's on both sides. It's really kind of the only way we can kind of proceed with this, because absolute values, keep in mind, we have to isolate those. That's our goal, is to isolate this absolute value. We would next divide both sides by 2, in which case we end up then with the absolute value of x minus 2 is equal to negative, really this is 1/2 x plus 1/2. Now that we have an absolute value is equal to something, we can go ahead and do a split. So in one of them, we have x minus 2 is equal to this negative 1/2 x plus 2, or plus 1/2. For our other one, we have x minus 2 is equal to the negative of this entire side. So negative 1/2 x plus 1/2. Because again, anytime you have an absolute value equals something, that's when you can go ahead and do your split, where one of them's positive of everything and the other is negative of whatever that is on the other side. Over here, now we've got actually 2 different functions. We would just have x minus 2 is equal to negative 1/2 x plus 1/2, just kind of rewriting it and then adding 2 to both sides, so then x is equal to negative 1/2 x. Looks like plus, if you add 2, you'd end up with 2.5, which is the same thing as saying 5/2. And now we can go ahead and add this 1/2 x to both sides, kind of getting all those x's on the same side and numbers on the other. So when we add a 1/2 x, over here they cancel out. X plus a 1/2 x gives us 3/2 x, or 1.5 x. And that's equal to 5/2. Multiplying both sides by 2 just to clear this fraction, we have the 2's canceling out, leaving us with our 3x is equal to, on the right side they cancel out as well, leaving us with just 5. So it looks like then x comes out to be 5/3. Now for the right one, we're going to do pretty much the exact same set of steps. We only have a negative that we have to distribute first. So we have x minus 2 is equal to 1/2 x minus 1/2. You could even multiply 2 right here if you really wanted to. It doesn't matter. In fact, let's just go ahead and do that. Let's multiply both sides by 2. Kind of clear that fraction. On the left side, we end up with 2x minus 4 is equal to, on the right side, we end up with the 1/2 canceling out with the 2 when you distribute that in, leaving you with just x. And then minus a 1/2 of 2 is just 1. Now no fractions at all. Now when you're trying to solve for x, you would subtract x from both sides, leaving us then with 1x on the left. Minus 4 is equal to negative 1. Add 4 to both sides. Looks like x comes out to be 3. Now at this point, we have to actually go ahead and take our x values and throw them into this part of our function to see if we actually end up with any extraneous solutions. Now an extraneous solution, again, you may or may not recall, is basically a solution that just doesn't work out. No matter what you've done algebraically to find him, he comes out to be some x value, and in the end, if you recheck it, it doesn't quite work. So let's go ahead and check our 5/3 one first. So we have the absolute value of 5/3 minus 2. Is that equal to negative 1/2 x plus 1/2? Well, 5/3 minus 2 is the same thing as saying 1 and 2/3 minus 2. Is this equal to negative 1/2? Now that we have both x's, we actually have to go back and check to see if we have any extraneous solutions. So we're going to throw in our x's in here to see if they come out to in fact be that true statement, that the left side is matching the right side. So we'll start off with our 5/3. And we have the absolute value of 5/3 minus 2. Is that equal to negative 1/2 times 5/3 plus 1/2? 5/3 minus 2, we can actually do a little bit of foo here with this 2, multiplying the top by 3 and the bottom by 3, such then where you end up with 5/3 minus 6/3, to then be able to go ahead and combine these since they now have the same bottom. Is that equal to, on the right side we have negative 1 times 5, that's negative 5. On the bottom we have 6. Plus, doing a little bit of foo as well over here with 1/2, we'll multiply the top and bottom both by 3 over 3 to then get 3 over 6, such then that we can go ahead and combine these on the right side as well. In our absolute value, we have 5 minus 6. That's negative 1 over 3. Is that equal to negative 5 plus 3 gives us negative 2, 6. And then the absolute value of negative 1/3 comes out to be positive 1/3. is that equal to negative 2 divided by 6? That can be simplified down to negative 1/3. And unfortunately, 1/3 is not equal to negative 1/3, and as a result, this would be an extraneous solution. In other words, you've done everything mathematically correct, but unfortunately, when you go back and try to plug it back into the original, it doesn't quite work like we just saw. So this guy would not be a solution. Next, we can go ahead and try our other guy, x equaling 3. Throwing that into our equivalent statement, we have the absolute value of 3 minus 2. Is that equal to negative 1/2 times 3 plus 1/2? 3 minus 2 will just come out to be 1 inside of our absolute value. Is that equal to negative 1 times 3 gives us negative 3 over 2 plus 1 over 2. Absolute value of 1 is just 1. Is that equal to negative 3 plus 1 gives us negative 2 over 2. And even here, unfortunately, it looks like negative 2 divided by 2 comes out to be negative 1, which these are not equal. So as a result, this x equaling 3 comes out to be an extraneous solution as well. Now again, we've really gone through every correct step when we've been talking about absolute values, and everything algebraically that we've done to find those x values has been correct, and even when we go back and plug them in, all of our algebra is correct. But unfortunately, you end up with these extraneous solutions such then that they don't actually work out. So graphically, what's going on here is you have some v, and we know that it's opening down because that a value is down. And then you have this other line, and you're hoping that it's going to cross through these 2 points, but unfortunately it's probably above this line, so it's doing something like this. It will never cross then our absolute value. Now, just going ahead and taking out our TI-84 calculator to kind of prove this point, just to kind of show you how to manipulate and find some of these intercepts that might be a little more difficult. Let's go ahead and take out the 84. We first have to tell the calculator what our functions are. So we're going to go to y equals, and then we're going to type in our function. We have, for the first one, negative absolute value. To pull up an absolute value, you're going to hit math, scroll over to num, and notice the first option is ABS. That stands for absolute value, and then it has like an opening parentheses. We want to pull up an absolute value. Then our function says it's x minus 2, so right here is our x minus 2. Now to get outside of the absolute value, we need to scroll out of it, and then at the end we have plus 3. So there we've told our calculator for this first function, here it is. Now we also have to tell the calculator our other function. Now unfortunately, we don't have things in terms of like a y equals mx plus b. Right now, we actually have things in standard form for our second function, so we actually have to go ahead and solve for y equals mx plus b here. We would first, there's a couple ways you could do it. We would first maybe subtract x from both sides. So negative 2y is equal to negative x minus 5. And then divide both sides by negative 2. So then y is equal to negative 1 divided by negative 2 would be a regular 1 over 2. X. Negative 5 divided by negative 2 would give us a positive 5 over 2. So in terms of y equals mx plus b, that would be our function for the second one, for the line. So then we have y equals parenthesis 1 divided by 2, close parenthesis x, plus open parenthesis 5 divided by 2, close parenthesis. So now we've entered both functions into our graphing calculator. Going ahead now and hitting graph, and there you can even see that they are not crossing. All right. But again, that is example 11 from our 3.1, 3.2 set of notes.